So now we're going to look at finding the intersection of two lines. So in the content, you should have realized that two lines can intersect never, so there'd be no solution. They can intersect once if they're not parallel, so there would be a point or one solution, or they can be the same line. So that's parallel and coincident, and then the lines themselves are the solution. There's an infinite number of solutions because they touch everywhere. Now, this system should look familiar going back to grade 10. It's just a system of two lines, and we're going to solve it. Probably the best way is to solve by substitution, so I'm going to do that first, but I'm going to do a quick review of elimination as well because it's another option. So I have two equations, equation 1 and equation 2. I'm going to take equation 2 and isolate the x. This is the best choice because the leading coefficient is 1. Every other variable, if I try to isolate it, I'm going to be involved in a division, and it may or may not work out well. But equation 2 works out to be x is 2y minus 13 if I isolate the x by bringing everything to the other side. And then I'm going to sub for x in equation 1. So equation 1 is 2x plus 3y minus 30 equals 0. But instead of x, now I can write 2y minus 13. And now I'm just going to work it out and do the math in order to solve for y. So I get 4y minus 26 plus 3y minus 30 equals 0. So 7y equals 56, y equals 8. And then I'm going to use this back in here. So x is 2y minus 13, which is 2 times 8 subtract 13, which gives me 3. So therefore, the point of intersection is x is first 3, and then y is second 8. So that's substitution. Elimination goes back to this where I have 2x, 3y. If I multiply the second equation times 2, I will also have 2x. So I'm going to keep the first equation the same, which is 2x plus 3y minus 30 equals 0. Then I'm going to take the second equation and double everything. So I end up with 2x minus 4y plus 26 equals 0. Now if I look at what I have two equations with the same number of x's. These x's have the same sign, so I'm going to subtract them to eliminate the x's. That's why it's called elimination. So 2x take away 2x is gone. 3y take away negative 4y is 7y. Negative 30 take away 26 is negative 56. So when I finish solving for y, I get 8 again. Now I would have to go back up to one of these equations. I can also go back up and grab this one, which I probably will use because it's the easiest. And so I had x minus 2y plus 13 equals 0. So x minus 2 times 8 plus 13 equals 0, which gives me x equal to 3, and I get the same answer. We use substitution the most as we move through higher grades because it works if your system doesn't consist of like things. So let's say I was solving a line in a parabola. Substitution works. In order to do elimination, you have to have the same type of equations, but it is an option. So feel free to use elimination if it works for any of the examples in your homework. I tend to use substitution, again, because it is the most versatile. Okay, so that's when lines are in standard or scalar form, but what happens if they're in vector form? So still a linear system, it's still the same type of situation you learned about in grade 9, 10, and 11, but now our lines are given to us in a little bit different form. What I need to really do is switch these into parametric form. So from equation 1, x is 18 plus 3t, and y is negative 2 minus 2t. I just took the information from the first line and put the x bits together, and then I put the y bits together. I'm going to do the same thing for the second equation. So x equals negative 5 plus 2s, and y equals 4 plus s. So now I've just transformed the forms into parametric, because at the point of intersection, if there is one, x equals x, and y will equal y. So I'm going to set those equal to each other. So 18 plus 3t would have to equal negative 5 plus 2s, and negative 2 minus 2t would have to equal 4 plus s. So now I have two equations, but instead of solving directly for x and y, I'm solving for s and t, which is the parameters, which then I will use to find the x and y for my solution. I'm going to do substitution. I've looked at that variable there because it's going to be very easy for me to get the s by itself. Doesn't matter the order you number them in, so I'm going to sub for s in the other equation. So then I get 18 plus 3t equals negative 5 plus 2 times s, but s is negative 6 minus 2t. I'm going to keep working the math on this. So I'm going to get 7t is equal to negative 35. So t equals negative 5. And then I'm going to use that to find s. So then negative 6 minus 2 times negative 5 equals s. Do I really need it? I don't think I necessarily need the s in this case, because if I'm going to find the point with t, I'm going to go back up to the first set of equations because they work with t. So from that, x equals 18 plus 3t, so that's going to be 3 times negative 5, which is 3. And y is going to be negative 2 minus 2 times negative 5. Again, I'm just grabbing my parametric equations from the top and putting my parameter, t equal to negative 5, in. So that's going to give me 8. So the solution is 3, 8. If we check, if I use negative 17 in here, it should give me the same answer, which it's not going to. So something's gone wrong. This is not negative 17. This is going to be 4. I calculated this wrong. Negative 2 times negative 5 is positive 10. Negative 6 plus 10 is 4. So if I put s equal to 4 up in here, I'll get x equal to negative 5 plus 2 times 4, which is 3, and y equals 4 plus 4, which is 8. Once I have the first parameter, t equal to negative 5, I really don't need the s in this case. But you'll see later on when we get into 3 dimensions, we always have to be wary of what's happening with the other values in the other parameter to go from there. So this solution is 3, 8. So when they're in vector form, you want to put them into parametric form and get your parameters. Okay, so question 3. I have 2 lines. They're already in parametric form, but the difference is now that we have the third dimension, we have the z. So this is where we need to be careful. I know at a point of intersection, the x's, the y's, and the z's have to be the same. So I'm going to start off by setting them equal to each other. So negative 1 plus 3t has to equal negative 1 plus 2s. 1 plus 4t has to equal 3s. And negative 2t has to equal negative 7 plus s. Now, in order to solve a system, you need as many equations as you have variables. I now have 2 variables, s and t, that I need to solve with. But I have 3 equations. Here's where we have to be careful, because when I take 2 of them and solve them, because I only have 2 equations, if the lines are not parallel, they will always intersect and you will get a point. The problem is when you bring the third dimension in, it's possible for them to be skew and they will miss each other. So what you're going to do is you're going to pick 2 to solve. It doesn't matter which 2. I honed in on this one right away because it has s by itself. So I've decided I'm going to solve these 2. You can solve any 2. I just picked this one because it was beside it. So this is going to give me s is 7 minus 2t. So that's my first equation. That's my second equation. And I'm going to sub for s in the other. So I get 1 plus 4t equals 3 times 7 minus 2t. I'm going to do the math to figure out what t is. So 10t equals 20, so t equals 2. So I got a solution, but the problem is if I just take t equal to 2 and put it in here, the lines could actually be intersecting or they could be missing. So what you need to do is in 3 dimensions, you find your t. You need to find the other parameter as well, and this is why the last time I found the other parameter. But in 2 dimensions, you don't need both parameters. But in 3 dimensions, I need to find both of them. So I get s is equal to 3. Because even if these lines are skew, when you pick 2 of them and solve them, if they're not parallel, it's going to look like there's a solution. So now we have to take these numbers and check in the third to see if these parameters actually work. So we're going to check in the remaining equation. So you find your two parameters, and then you go back to whatever equation you didn't use and you put them in. So t was 2, and s was 3. So negative 1 plus 3 times 2 is 5. Negative 1 plus 2 times 3 is 5. So this works. So that means the lines do intersect. If I got 5 is equal to 0, or negative 1 is equal to 10, if you get something here that doesn't work, it means that the lines are skew and they don't intersect, and you'd say therefore no solution. But because our parameters work, now I'm going to pick one. I'm going to pick t equal to 2 and put it up in here. You could put s in there. It really doesn't matter. But now, because I know they intersect, I'm going to use t equal to 2 and go back up and grab my first set of parametric equations. So then x is negative 1 plus 3 times 2, which is 5. Y is 1 plus 4 times 2, which is 9. And z is negative 2 times 2, which is negative 4. So, therefore, the point of intersection is 5, 9, negative 4. If you've solved both parameters and they don't work in the third, that means the lines are skew and there is no point of intersection. So let's do one more in 3 dimensions. And this time it's given to us in vector form, so I actually have to go through and make up the parametric equations. So x equals 2 plus t, y equals 1 minus t, z equals t, and x equals 3 plus 2s, y equals 3s, and z equals negative 1 minus s. And then I'm going to put them equal to each other. Now, some people skip this and they go right from here and say 2 plus 1t has to equal 3 plus 2s. That's fine, whatever you're comfortable with. So 2 plus t equals 3 plus 2s, 1 minus t equals 3s, and t equals negative 1 minus s. Again, I honed in on this equation right away because it already has the t isolated. So I've decided I'm going to work with these two because this one is right beside. So I'm going to get 1 minus negative 1 minus s equals 3s. It's a negative t, so I have to be sure to put the negative 1 minus s in a bracket. So this is going to give me 2 plus s equals 3s. So s equals 1. Make sure I did that right. That's going to be plus 1. That's going to be plus an s. And then that's going to give me t equal to negative 2. Negative 1, subtract 1. I'm going to check them over here, so I have those answers, but I need to check to see if the lines actually intersect or if they are skew. So 2 plus negative 2 equal to 3 plus 2 times 1, and I can already see that this does not equal, so therefore the lines are skew and there's no point of intersection or no solution. So the key is when you have 3 dimensions, when you ignore one of the equations to work with 2, you're bringing a system that was in 3 dimensions back to 2 dimensions, and they will always cross. So that's why you have to go back and check that 3rd dimension to see, do they actually in fact cross, or does the 3rd dimension pull them apart?